Okay, thanks, Gerard. So Gerard said that doing interferometry from the ground was a pain in the rear. And so I'm going to cover some of the reasons as to why that's the case, sort of slightly at a pedagogical level. But the biggest challenge, of course, to doing interferometry from the ground is the clear turbulent atmosphere. So why, you might ask, is if I am a plane wave propagating through the atmosphere, would I care about whether it's turbulent? And it's because the wave actually has electromagnetic interactions with the medium in the atmosphere, right? Because the medium has a refractive index, and the turbulence leads to little microfluctuations in temperature, which lead to index fluctuations on all sorts of scales. And so these index fluctuations then show up as amplitude and phase fluctuations in the incoming wavefront. Okay. So for an interferometer on the ground, the turbulence exists basically everywhere. It's inside your instrument. It's in the systems that transport your light, unless you can transport it in vacuum somehow. It's on the ground at the boundary layer, a few hundred meters above you. It's in your domes. It's above your mirrors, et cetera, et cetera. And then, of course, it also exists at very high altitudes up in the jet stream. So this is the faster form of turbulence associated with high wind speeds. The strength of turbulence is often parameterized with this kind of a simple model. It's called the Hufnagel Valley model. And this kind of gives you an idea of how the strength of turbulence varies with altitude in the atmosphere. If you're in the stratosphere above 20 kilometers, you're essentially left with nothing. But it's not just turbulence. Interferometry also derives challenges just from the still atmosphere itself. This is true, of course, not just of interferometry, but also adaptive optics and astronomy in general. You are sitting inside a fluid which has a complex index of refraction. The imaginary part of that index of refraction is associated with absorption. The real part is associated with the phase of the electromagnetic wave that's propagating. You have scattering at short wavelengths. You have absorption from induced polarity in molecules at optical and IR wavelengths. And then you have absorptions from the permanent dipole of water at longer wavelengths, which is basically what creates this region from the far IR to millimeter waves, where we're mostly blind, at least from the surface. So absorption, of course, leaves us with little atmospheric windows to work with, but each of these little transitions that cause absorption also result in phase delays, basically because the real and the imaginary part of the refractive index are related to each other through relationships. Okay, so these propagation delays mean that you have a geometric delay, which is up in vacuum in a plane parallel atmosphere, whereas you compensate for that delay, as Gerard said, with delay lines in air. And that essentially causes problems with dispersive delays within bands, dispersive delays at two different colors, et cetera, which can make life difficult, even if you didn't have to worry about turbulence at all. But back to turbulence, the fact that the clear turbulent atmosphere causes phase and amplitude fluctuation results in coherence limitations. Okay. So coherence limitations mean that you can only work with small apertures over which the wavefront is coherent. And the size of that aperture is what's called an R0 in the language of wave propagation in random media, essentially. So with the visible, you can work with apertures that are about 10 centimeters across for it to be coherent. But then not only that, you are also limited in how long you can integrate on your detector. And that is determined by what's called the coherence time, which is determined by, once again, this R0 sized quantity, which is 10 centimeters, and the speed at which the wind blows the turbulence across your aperture. And so your photon rate times this kind of coherence volume, essentially, has to be greater than 1. You have to have at least 1 photon to detect your fringe, which puts a hard limit on how faint an interferometer can really go with no assistance at all. And so this is typically about a V magnitude of 10. All of these quantities, the R0 scale is lambda to the 6/5 roughly. And so things ease up as you go into the IR. By the time you're in the thermal IR at 10 microns, lambda to the 6/5 is a factor of about 30. And so the coherence volume goes up by the cube of that, roughly. The overcoming the coherence limitations with larger apertures, of course, can be done with adaptive optics, but you still have the limitation of the coherence time. And one way of overcoming this coherence limitation is with interferometric phase referencing. Short coherence times limit the phase tracking interferometers, even on 8 to 10 meter class telescopes, to basically 10th, 11th, 12th magnitudes, I think. We have not been able to, unless I'm wrong, we have not been able to do better than that. Off-axis phase tracking or phase referencing can be implemented to realize longer coherence times, up to, say, minutes or something, to observe fainter targets. And so the requirement there, of course, is that sources A and B have to be within a few arc seconds of each other, within an angle which is called the isoplanatic angle. So these angles are there in the interferometry literature. They're there in the adaptive optics literature. So many people should be familiar with them. This kind of phase referencing was first implemented here at Palomar on the PTI, then at the Keck interferometer, and then finally at the VLTI in Prima. But it really has been scientifically exploited, I think, for the first time with the gravity instrument, where I think phase coherent integration times can be up to a minute or even longer, unless I'm really wrong. Another way to overcome some of these atmospheric limitations is to measure quantities called closure phases, which are, closure phase is essentially summing the phases across a triangle in an array of telescopes. Okay. So if you had an array of telescopes, you can measure n combinations 2 unique phases. Okay, so that's the number of baselines. So that's the number of phases you can really measure. However, you can also measure not n combinations 3, but n minus 1 combinations 2 closure phases in your array of telescopes. Okay, n combinations 3 is actually bigger than n combinations 2 for most. But if you think about it, you'll come to the conclusion that it's actually n minus 1 combinations 2. So given that the ratio of observables in closure phase measurements is roughly n minus 2 over n. So I just taken the ratio of those numbers here. which is only about 33% if you're working with just 3 telescopes. Okay. However, it can be quite a large number. It's almost 100% when n goes to infinity. So if you have an array with many, many telescopes, you essentially have most of the phase information in the closure phases. So in general, the reliability, when you're talking about imaging with interferometric arrays, favors a large number of telescopes for more robust calibration of the images and for better UV coverage, of course, as well. This is something that may actually be done easier from the ground than in space because the ability to build arrays with 20, 30 telescopes, etc. Finally, just to come back to nulling, which is essentially the technique that we are going to talk about most in this meeting. Nulling from the ground has only been done in pursuit of measuring exozodiacal light around nearby sun-like stars, actually as part of planning for these future coronagraphic or interferometric missions. The contrast of one exozodiacal disk to a star at 10 microns is about 5 times. It's about 50 parts per million, I guess. It's 5 times 10 to the minus 5. If I reverse this into the measurable that Gerard talked about for interferometers, which is visibility, you can write the null as 1 minus v over 1 plus v, and that means you essentially have to measure your visibility to about 100 parts per million, which is actually a pretty calibrated visibility, which is quite a difficult measurement at any wavelength, optical, IR, or even radio. In practice, I would say ground-based nullers have achieved a factor of 5, maybe a factor of 10, worse than that. But that itself is a pretty remarkable achievement. These measurements are done close to the star. I mean, they're a tenth of an arc second is roughly where you're looking for. It's an AU disk at 10 parsec. And so you're working at pretty close angles. For planets, a similar sort of thing can be translated to a visibility calibration need of about 1 part per million. So it's a factor of 100 more difficult problem. From the ground, the nulling is analogous to essentially coronography. Okay, so you have the same sorts of errors. You have dynamic errors from the atmosphere, phase and amplitude fluctuations. You have quasi-static errors from your instrument that you need to, and you have cross terms between quasi-static errors and dynamic errors, and they all need to be figured out. You can have amplitude, phase, polarization, all kinds of errors. And so just to write the more important ones, which is the amplitude and the phase, those who do coronography will be familiar with these variance type error terms, plus a myriad other terms, which means that if you want to measure a raw null of about 10 to the minus 4, you actually have to fringe track, or control the phase in the instrument to about 30 nanometers RMS. That's actually quite difficult. It was never really possible at the Keck interferometer. And I don't think that it really is possible at the VLTI as well. First of all, the vibration environment will have to be fixed in order to get there. Another thing is the background rates when working in the thermal infrared are huge. I mean, we all know this, right? The raw null depth can be limited by improper calibration of the background. So then I can write my raw null again with one extra term, which is the essentially how well I need to know my background. And it turns out I need to know my background to about a part per million in order to do this right, which took the Keck interferometer nuller through various hoops, making it a fairly complicated machine. Probably a slightly easier problem with its wider field of view for the LBTI, which is why, but nevertheless, a difficult problem. So I have to finish up soon. We can't be standing here right under Mount Wilson without discussing the role of that observatory to the history of interferometry, which of course, starts with exactly one pandemic ago, with Michelson and Pease in 1921. I think the pandemic ended in 1920. So we're ripe for another revolution in interferometry, 100 years. So we start with a 20-foot interferometer, essentially a cross beam over the 100-inch telescope, which is used as a Fizeau interferometer. It's basically a beam combiner and a pointer, the 100-inch telescope in that case. And I think you'll see some of this next Wednesday. They made the first important measurement of Betelgeuse, and then went on to make diameter measurements of a total of 6 stars, followed by Pease's interferometer in the 30s, which never really worked, and probably which is what put an end to interferometry on Mount Wilson for a little while. In the meantime, there were very important developments, especially with Hanbury-Brown and Twiss, which is very important in physics. The quantization of the electromagnetic field and all of that stuff started right after that. And then, of course, the fringes that Laborie obtained in France with 2 separated telescopes across a 12-meter baseline on Vega. That restarted work on Mount Wilson in the 80s, which continues till today, with the Mark 1, 2, and 3 stellar interferometers, which introduced a lot of the modern techniques that we use in interferometry today. It relied on significant advances in optics, electronics, computing, lasers, etc. Mark 1 demonstrates phase tracking. Mark 2 demonstrates the use of fast delay lines like the kind that Gerard showed. And Mark 3 shows 2-color astrometric measurements. This is followed by the world's highest frequency radio interferometer of Towns et al., which worked at 11 microns and used a carbon dioxide laser as a local oscillator and a total bandwidth of 3 gigahertz, roughly. This operated on the mountain from about 1988, I think. I'm not quite sure. But then it's still up there, and I don't know if that's part of the tour or not, but you can see it. And then finally, you have the Chara array, which of course is the most important facility, at least in this country today, and is a major facility for testbed of technologies, so beam combiner technologies and other crazy stuff, which I hear is going on the mountain. So with that, let me come to my last slide about new challenges in ground-based interferometry. Of course, the desire is to go to longer baselines than what we have currently topographically limited on mountains like Chara and so on and so forth, maybe up to a kilometer, maybe wider. So some areas that I want to leave behind are making the combination of light a little bit simpler, especially in the IR, by the development of photonic combiners in sort of the mid-IR bands. Fiber transport, potentially, from long distances, and maybe even fiber delay lines. Fibers are strongly dispersive media. Again, a pain in the rear. So that makes all of these things look really hard. And apart from silica fiber and perhaps Z-bland glass, transmission in fibers is still quite poor. And so, there may be new technologies out there with sort of hollow core fibers or hollow core photonic fibers that guide light in hollow cores using photonic structures around them. For long baselines, maybe like 10 kilometers or 100 kilometers, we can maybe start thinking in terms of heterodyne combination again. I know that JB and others are interested in this. And so there are various technologies here, like building broadband heterodyne photonic receivers, time transfer for syncing local oscillators, et cetera, the local oscillators themselves. And then, of course, if you really can build broadband heterodyne receivers to increase the signal-noise ratio of heterodyne detection, then that's a lot of data, especially if you digitize it. So you have to think about computing the correlators, et cetera, or maybe just ultra-high-speed data recording. So with that, I will end this talk. Thank you.